Hi students, how is everyone doing? Oh, let's start. So, in today's lesson, we are going to do a certain kind of problems where we are either taking a situation where we have to keep certain objects together, or certain objects, as the title says, bundle and gap. Bundle stands for when certain objects have to stay together, or gap when there has to be a gap between certain objects. Those objects can never be together. If you remember from our previous class, we did consider one of those cases when one particular boy and one particular girl could never be together. There always had to be, in a way, a gap between them. So now, in case we have to arrange those students where we have to keep certain students together, or we have to maintain a gap between certain students, they can never stand next to each other. So for example, such cases can be handled using bundle method or gap method. It's very easy, very logical. We'll just understand how to go through those scenarios, how to make sure we're counting all the cases, excluding all the right cases, and you're going to find that kind of questions very easy by the end of this lesson. Alright. So first of all, we're going to start with bundle method. Bundle, as I mentioned, certain objects have to stay together. Let's take a look at this example. A library has 3 mathematics, 2 physics and 5 chemistry books, which are to be arranged on a shelf. In how many ways these can be arranged such that all books of same subject are together? These 3 stay together, these 2 stay together, and these 5 stay together. Now, we have 2 options. Either these books are identical. For example, they're all NCERTs. We just have 3 different copies of maths NCERTs, 2 different copies of physics NCERTs, 5 copies of chemistry NCERTs, but they're same book. In which case, it won't matter what order these books are in. It's the same situation. But the second case, they are distinct. Books of same subject are also distinct. That means we have 5 different kind of chemistry books, 3 different kinds of maths books, in which case the order is going to matter, right? So let's take a look at this one by one. One thing that stays common, the bundle, we have to form the bundle. Let's see. So the first case, when books of same subject are identical, that means we have 3 maths books, 2 physics books and 5 chemistry books. Now these 3 have to stay together. That means this is one bundle. These 2 have to stay together, this is one bundle, and these 5 have to stay together, so this is one bundle. In total, we have 3 bundles with us. Now the order can be this M bundle, this P bundle, this C bundle. The order can be PMC, MPC, MCP and so on. Because they are identical, it doesn't matter how we are arranging these 3 maths books as long as the bundle is together, because the books of same subject have to stay together. So we just have to arrange these 3 bundles, which means 3 factorial. So as soon as we find one arrangement of M, P and C, we know what order these books are in, because the M represents the M bundle, P represents the P bundle, C represents the C bundle, or I like to call it, instead of bundle, unit. So this is one unit, this is one unit, this is one unit. Now we have to arrange 3 different units. But in the other case, when the books are distinct, now this is M1, M2, M3. This is the M unit or M bundle. Then there was P1, P2, the P bundle, and C1, C2, C3, C4, C5. The C bundle. Now, just like before, we have to arrange these bundles. Yes. So, 3 factorial. But as soon as we arrange the bundle, that does not guarantee that we have a unique arrangement, because within the bundle, this M1, M2, M3 can be arranged in 3 factorial ways. Within this bundle, P1, P2 can be arranged in 2 factorial ways, and C1, C2, C3, C4, C5, these can be arranged in 5 factorial ways. So for each of these arrangements, we will have this many arrangements for each of these. So 3 factorial multiplied by the number of arrangements possible within each bundle or unit. So this will be the final answer. So just to reiterate, what we did was, whenever we have to make sure that certain things are always together, we keep them together. Now you are together, you act as one unit. Now we arrange this one unit along with the other objects, and if within that unit there can be multiple arrangements, we multiply the total number of arrangements with that smaller number of arrangements which can happen within the unit. Okay, let's take a look at another example. If now earlier all these books of same subject had to be together, like M books had to be together, P books had to be together, and C books had to be together. Now we only have the condition that mathematics books are together. The rest can be anywhere. We just care about mathematics books. They should be together. All 3 of them should be together. Now we only have one maths unit and 2 separate physics units, because each unit for its own, they can be together, they can be separate, they can be arranged in any way. And similarly 5 different chemistry books. So now we have M1, M2, M3, and then P1, P2, C1, C2, like this. This is one unit. So how many total things to arrange, total objects to arrange? This one unit, and 1, 2, 3, 4, 5, 6, 7. So 2 plus 5, 7, plus 1, 8. So now we have to arrange these 8 factorial objects. But in the first case, books of same subject are identical. In that case, books of same subject are identical, which means, if you remember from the permutation lecture, P1 and P2 are identical. We have 2 identical P's and 5 identical C's. So divided by 2 factorial, 5 factorial. Right? Because P1, P2 are identical, so we just divided by 2 factorial and 5 factorial. Now if books of same subject are distinct, then we arrange these 8 units, 8 factorial, and now we also have to arrange within the unit. So multiplied by 3 factorial. Simply, logically, this is how you handle such problems. Okay, so students are giving the answers. If you want, yes, you can calculate. So this comes out to be 876 by 2. I cancelled 5 factorial. So that becomes 21 into 8, 168. And here, a big number. So 8 factorial would be, I know until 6 factorial, 720. So 8 into 7 into 720 into 3, a big number, as I said. So yes, okay, why did we multiply with 3 factorial? But just like before, we arranged all these 1, 2, 3, 4, 5, 6, 7 and this one unit 8. But that doesn't guarantee that we get all the arrangements. We can also have M2, M1, M3, M3, M1, M2. So for each of those arrangements within the unit, we can have 6 arrangements for every arrangement of these 8 things. The only thing that changes in such problems is we treat this as one new object, and then we just make sure that within this one new object, can there be multiple arrangements? If yes, then we multiply that 3 factorial. If not, then we just don't multiply anything. That is one object, just like before. So here the M books were identical. That means only one arrangement is possible, M, M, M. There is no M1, M2, M3. All three are identical. So we did not have to multiply with anything. This one object is just one object. Okay. Let's take a look at more problems. You will get more clarity. Okay. So now we have a word imagination, and we need to arrange the letters of this word, and we have 4 problems related to it. So first of all, if you remember from the previous class, what is the first step of such problems? We count all the number of letters in this. Okay. So we have I, then M, then A, G, then I, then N, A, T, then I, then O and N, just to get the right count of letters. So if we had to arrange all the letters of this, just see how many permutations are possible. We'll just count them all. 3 plus 1 4 plus 2 6 plus 1 7 plus 2 9 plus 1 plus 1 11. So 11 factorial divided by, these are tally marks bache, in case someone is getting confused, this is not 11, this is 2. Okay, I was just using tally marks to count the number of letters, the number of appearances of each letter. Okay, so 11 factorial divided by 3 for I, then 2 for A and 2 for N. Okay, so these are the total number of arrangements that we can have for these letters. Now let's take a look at the special cases that needs to be handled. Now our first condition is both A's are together. We have 2 A's, they have to be together. The rest can be in any form, but these 2 A's belong together, which means now instead of 2 A's, we have 1 unit AA. Because 2 A's are identical, there is no difference between the first A and the second A, then we don't need to arrange within this unit, but now this acts as 1 unit. Earlier we were arranging 11 things, now we will arrange 10 things. Instead of 2 A's, we have 1 AA unit. So we will arrange 10 things. And now how many repetitions do we have? Now this is 1 unit. There are not 2 different A's, so we will not divide 2 factorial for this. This is just 1 unit. It acts as 1 object. The rest we have 3 factorial for I's and 2 factorial for N's. Okay. Next problem. Both A's, both N's and all 3 I's are together. That means these 3 I's are also 1 unit now. And these 2 N's are also 1 unit now. They all don't have to be together. Just I's have to be together with each other. A's have to be with each other. N's have to be with each other. Now how many units do we have in total? How many objects do we have to arrange? 1, instead of 3 we have 1, plus 1, 2, plus 1, 3, plus 1, 4, plus 1, 5, plus 6, plus 7. So now we only have 7 objects to arrange. Okay. So now we have 7 objects to arrange, and because there are no repetitions left, that is it. Is that clear to everyone? Now let's take a look at the next condition. Now we are saying all vowels have to be together. Now, okay, there's a bit of chaos there, so let's write them again, except this time we put the vowels in 1 unit. So what all vowels do we have? We have 3 I's. Now they are not saying that the 3 I's have to be together. I's can be arranged in any way as long as it's next to a vowel. Okay. So 3 I's, then we have 2 A's and 1 O. So in total we have 6 vowels and the remaining consonants M, G, N, N and T. So now how many things to arrange? 1 unit plus 2 plus 3 plus 4 plus 5 plus 6. 6 objects to arrange. So 6 factorial. Now we were arranging these 6 objects, but there is a repetition. 2 objects are of the same kind. The rest are different, but 2 objects are of the same kind. So we will divide this by 2 factorial. And we have to check within this unit, can there be multiple arrangements? Certainly can. How many? 6 factorial divided by 3 for I's, 2 for A's. And this is your final answer. It is not a recorded lecture. What reply? What do you want to ask? Yes. So Karthik, your answer is correct. Yes. Yeah, a lot of you are giving correct answers. That is correct. Clear to everyone. If you have any doubts, that's the whole point of a live lecture, a live class. If you have any doubts, if you have a problem understanding any part of it, feel free to ask. Why did we divide with 2 factorial? But you see, now, okay, for those students who have a problem understanding this, let's look at it this way. I call this unit, this object, my unit vowel. Okay. What other objects do I have to arrange? 1 of M, 1 of G, 1 of N, another 1 of N and another 1 of T. Right? So 1, 2, 3, 4, 5, 6. I have to arrange these 6 objects. So 6 factorial. But 2 of them are identical. We remember from our permutation lecture that whenever we have a repetition, we have to divide it by the number of repetitions there are, right? So because the n is appearing twice, we have to divide it by 2 factorial. If you still have some doubts, bacha, I recommend that you re-watch the permutation lecture. You keep revising this. If this is all very new to you, you might be forgetting some topics. It's okay. Just revise the old topics before coming to the new class. Okay. So that is why we arrange this. But this one unit is not unique. It can be I, A0, or O can be here, or I's can be separated. It has multiple possibilities. How do we calculate the number of possibilities? 6 factorial by the I's were repeated 3 times. By 3 factorial, A's are repeated 2 times. So 2 factorial as well. And this is how we get the answer. Very logically, step by step, make sure you're considering all cases. That is all PNC is about. Combinatorics is about counting all the cases. Okay, now let's take a look at the last problem. All vowels are together and all consonants are together. Now, how is it different from our previous case? From our previous case, these vowels had to be together, but it could be between the consonants as well. The consonants could have been separated, but we also want the consonants to be together, which means we have our old unit I, A's, O, and we have another unit because consonants have to be together. So M, G, N, and T. Now we have 2 units. So 2 factorial. Within first unit, how many arrangements can be there? 6 factorial by 3 factorial, 2 factorial. Within the second unit, 5 factorial by 2 factorial. And this is how we calculate the number of cases. It's a tough question. It's okay. It's not tough. Trust me. It's not tough. It's just new. Okay, there's a difference between new and tough. It might be new, it might not be as obvious as our old lectures. As I mentioned, it is only going to get harder and harder. That means you have to revise before coming to the class. You have to revise. If you're not 100% confident on your old concepts, then understanding a new concept will seem very difficult. But if we take it one step at a time, making sure the old steps are perfect, then the new step becomes very easy. It's okay. Take your time, revise, understand at your own pace, but make sure you understand. So, just to repeat the last one, all vowels have to be together, which means there has to be a unit, a bundle of vowels. All consonants are together, there has to be a bundle or a unit of consonants. So, how many objects to arrange now? Only 2 units. So, 2 factorial. Now, within first unit, we get 6 factorial by 3 factorial, 2 factorial, and here we get 5 factorial by 2 factorial. That is the number of arrangements within the second unit. Okay. Now, gap method. This is to count the number of cases when we have to keep certain objects apart. Up until now, we were keeping certain objects together. We were bundling them together. Now we have to put a gap between those objects. Let's look at an example. Just like before, we have 3 maths, 2 physics, 5 chemistry books. Now the condition is maths books are separate. All these 3 books, no 2 of them should be together. There has to be a gap between the maths books. So, if we have something like, we arrange this. Let's say this is an arrangement of the rest of the books. Now, the maths books cannot be together, which means there has to be at least one of these books between the maths books, right? We cannot have MM like this here, because in that case, we will have the maths books together. We don't want that, which means there has to be at least one of these between 2 maths books. Now, it can be multiple of these between 2 maths books. That is also allowed, right? Or maths book can be here. That is also fine. Just that 2 books should not be together. 2 books should not go into the gaps between these books. So, what are we going to do? First, we are going to find the arrangement for the rest of the things. What are the rest of the things? 2 physics and 5 chemistry. Let's look at the first case. Same subject books are identical. Okay. So, no P1, P2, PP, CCC. Okay. So, that means how many arrangements can we have? 7 factorial divided by 2 factorial, 5 factorial. Right? Now, once we have an arrangement of P books and C books, we have to find some places to keep our M books. Where can these M books go? They can only go in the gaps between these. Now, how many gaps do we have? It can also be here or here, between the gaps, like this. So, how many of them are there? 8. One more than the objects that we had already placed, right? Because after every object that we had placed, there's one space and there's also one in the beginning. So, however you want to count, just one more than the objects we had already placed. In this case, we had placed 7 objects. So, this becomes 8 gaps. Out of these 8, we have to pick 3. Any 3. As soon as we pick 3 out of these 8 gaps, we have found our positions for the M books. And because we are only placing M books in different gaps, that means they are not together. So, this is the gap method. We arrange the rest of the things first, and then whichever objects need to be separate, we fill them between the gaps to make sure that they go in separate gaps. There is at least one other object between 2 of maths books. Okay. So this is how you get your 7 factorial by 2 factorial, 5 factorial into 8C3, the number of arrangements such that, first of all, maths books are identical to each other, physics books are identical to each other, chemistry books are identical to each other. In addition, no two maths books are together. All of the maths books are placed separately. Okay. Now let's take a look at the other case when same subject books are distinct, which means now we have P1, P2, C1, C2 and so on. So now, just like before, we are going to find an arrangement for the rest of the objects. In this case, because they are all unique, we just have to do a 7 factorial. No repetition, so no dividing by 2 factorial, 5 factorial. Okay. Now we have to place our maths books between these gaps, right? So out of these 8, we select 3. Additional thing now is, let's say I picked this, this and this. Let's say these are the 3 I selected. Now that doesn't mean that we are done here. Within these 3 gaps, there could also be another order when we just shuffle these like this. Now this is another unique arrangement because maths books are distinct. So within these 3 gaps, we have to arrange these 3 maths books, because there will be, once we have selected the gaps, we can still get 6 different arrangements. We have finalized the position of physics and chemistry books. We have finalized where maths books are going to go, and still we can arrange maths books within those gaps, right? Out of those 3, the first one could be M1, then M2, then M3, or it can be M2, M1, M3, M3, M1, M2. Like that, we can have 3 factorial arrangements for the maths books. So that is why we have to multiply the entire thing with 3 factorial. Yes, if you are able to follow along the entire course, if you are practicing, if you are understanding everything, if you are able to use your mind, you're not just listening, you're understanding and you're able to think on your own, then definitely you can solve any problem. Most of it we still struggle. There can be tricky questions. Combinatorics is not an easy topic, but still, yes, you will be able to solve all the questions if you're able to understand all of it. Okay, and able to think on your own. Don't just listen, think. If you want, you can pause later. Once you're revising, pause first, try to think on your own how we can count the number of cases and make sure you got the right answer. Okay, and even in case of new problems, don't look at the solutions directly. First, try to think on your own, develop that thinking capability, thinking habit. That is how you make sure your brain is active all the time. Your brain is able to apply whatever it has learned onto new questions. Okay, right? So this is how we do it. Now an interesting thing, I just can't move on without addressing this. This is nothing but 7C2, right? 7 factorial by 2 factorial, 5 factorial. This is clearly 7C2. Is this a coincidence that the number of arrangements of P's and C's was 7C2, or we could have got it directly from 7C2? See, we had to arrange 2P and 5C, right? How many arrangements? We did see that we arrange all of them 7 factorial and divided by 2 factorial and 5 factorial, we get it. But is there another way of looking at it? We first fix the 1, 2, 3, 4, 5. We first fix these 5 C's, right? This is a unique thing because they are all identical. We can just arrange them in one order. Now we have to place 2 P's. Now it can be anywhere. Here, let's first place the first P. Okay? P1, first we are placing. There's no difference between the first P and the second P. Just we are placing the first P and then we will place the second P. Because they are identical, we do not have to order them. Okay? So we can place them here or here or here. Anywhere. Right? The P has to go in one of these 6 spaces. Correct? Now, what about the other one? Where can it go? Either it can go okay. I hope you all are listening and not just talking in the chat. Okay. For all those students who are asking for guidance, by the way, we will have a separate session. We will have separate videos for that. This is a purely academic class. I know you want guidance. You are still somewhat struggling how to go about this journey, how to find the right path. I know that from time to time you need those guidance from your mentors, and we will have separate sessions for that. But right now we're just studying. Okay? You are listening? So I want you to reply as well. Right? First we place the P out of these 6. Right? Now, where can the second P go? We will not count this and this separately. Right? So P can either come here before all the C's, maybe the P is already there, or it can come here. Now let's say if P wasn't here, if P, we had placed the first P here, even in that case we won't count this one and this one separately, right? Because if we place the P here or here, it doesn't matter. There will be 2 P's between 2 C's and 3 C's. So it doesn't matter, we cannot treat them as a different thing, they are the same. So that means the second P also has 6 options, no matter where we place the P. Does that mean we have 36 cases? Does that mean we can have 36 possible arrangements? We earlier counted 7 factorial by 2 factorial, 5 factorial. How much is that? 7 into 6 into 5 factorial by 2 into 5 factorial. So this comes out to be 21. Here we are saying we have 36. Did we miss some cases there? Did we count some extra here? I want you all to actually think about it and reply to me now. So, for all those who weren't listening, who weren't paying attention, or who missed it somehow, what we did in this case, earlier we had counted that we can just arrange these 7 2P's and 5 C's in this way, 7 factorial, and then because there were 2 repetitions for P and 5 for C. So, we do 7 factorial by 2 factorial, 5 factorial, right? Now, we are saying that we have 5 C's. So we will put 5 C's. They will be there, right? Now both P's can be here or here or here, or they can be separate. We don't know, we have to count all the cases. So we first see where the first P can go. It can go either here or here or here, between the gaps, right? It has to go somewhere, right? Let's say we only had 5 C's and 1 P. In this case, even if we went by that logic, 6 factorial by 5 factorial for the 5 repetitions, that means 6. And even if we go by this method, we get 6 places to place our first P. Now what about the second P? I am saying the second P also has the same option, the same number of options. Right? If I had placed the second P here, then the first P here, then second P also has these 6 options. What am I counting extra in this? That seems correct, right? That seems like, yeah, that makes sense. We counted the number of permutations. We know that is the correct formula. We derived this formula the other day. We know that is the correct answer. Why are we getting 36 here? What is the extra that we are counting? Come on, think. I want some of you to answer. I'll answer. If you guys don't, I will tell you what is the extra. But yeah, whoever got it, yes, tell me which cases is, like, for example, just 2 cases which will be counted multiple times or twice. Yes, that is correct. No, I get it. What some students are saying is, I just want you to answer this one problem. I will tell you what we are counting multiple times. We are counting this P as my first P, and let's say I place the second one here. Now what if I had placed the first one here and the second one here? Because there is no difference between the two, then that means these are being counted twice. These are the cases that are being repeated. So bachche, this is what I'm trying to tell you. In combinatorics, it might seem like you're going the right way, but you have to be very careful that, are you sure you're not repeating any case? So yes, you guys are suggesting right, that what we can do is, we treat them as 2 separate P's. In which case, now there are 2 possibilities even here. Even when we have placed P1 here, then one can be before P1 or after P1, right? So we do that. We arrange, how many places will we have? Because we have already placed 6 things, we get 1 extra space. So 7 things now. We had already placed first P in 6 ways. Now we are finding 7 spaces for the second P. But they are not actually different. We treated them as 1 and 2, and we thought that their order matters. But the order doesn't matter, so we will divide it by 2 factorial. So this is the same. Yes. Now, why could we not divide this by 2? Why could we not just divide this by 2? Because we had not taken all of them. The total cases were 42. We had not taken all of them because we did not count these 2 as separate. Here we treated them as identical P's, but when we did not, so basically when we are placing them together, they are identical, but when we are placing them separately, then we counted those cases twice. So we had to actually check how many cases are there when the two of them are together, how many cases are there when the two of them are separate. The separate ones are being counted twice, so we'll just remove those. So in total, 6 ways of placing them together, right? If PP are together, then there are 6 spaces for P and P together, and the remaining 30 ways of being separate. So we only divide these by 2. So then we get 6 plus 15 equal to 21. So I'm just saying that whichever method you take, as long as you're being careful, you're removing all the repeated cases, you're counting all the missed cases, in that way you will get the same answer. The answer cannot be different. But why was it 7C2? Is that a coincidence? This is what I'm asking. Okay. Go home and think about it. We'll definitely answer this in the next class. I want you to expand your brain. Think about it on your own. I know you can reach the answer. We will think about it, okay? And we will discuss this in the next class. I want all of you to come prepared with this. Why? How is it 7C2? How can we reach this? How are we, what is it that we are selecting 2 out of total available 7, or maybe 5 out of total available 7? Okay, do think about it. Trust me, if you just keep hearing the solutions, it will definitely not help you as much as when you think of the solutions on your own, when you think of such things on your own, when you think of different methods of approaching the same problem on your own. Here we discussed 3 different ways of reaching the same answer, right? So just like that, I want all of you to think about this additional method. Anyway, continuing. So coming back about the gap thing. Whenever things have to be separate, we will first place the things that don't matter. They can be anywhere. So we place the P's and the C's, and then the M's had to be separate. So we have to fill them between the gaps. Okay. Now, coming back to our imagination word, both A's are separate now. If you guys need this, we'll do this again. But because I remember from the last time, and I'm sure you do too, to some extent, we have 3 I's, 2 A's, 2 N's, and the rest were 1 E, G, M, T, O. 1 each. Right? So 3 plus 4, 7 plus 4, 11. We had total 11 letters. This is what the count was for the word. Now, we need the condition when both A's are separate. Both A's are separate. Again, the total number of permutations for imagination will be 11 factorial by 3 factorial, 2 factorial, 2 factorial. These are the total number of words possible. Out of these, how many are there when both A's are separate? So we arrange the rest of them. Remove the 2, arrange the rest. 9 factorial divided by 3 factorial. I's are identical. And N's are identical. Now we have arranged the 9 things, right? Now we have arranged 9 things. That means we have 1 extra gap, 10 gaps. Out of those 10, we have to place the 2 A's. So we have to select 2 A's. Because the 2 A's are identical, we do not have to arrange the A's between the gaps. So this is our final answer. Right? Everyone gets this? Now, no 2 I's are together. No 2 I's are together. That means all 3 I's are separate. What do we do then? Achha, before we move on, both A's can either be separate or can be together. There's no other option, right? The 2 A's can either have some letters between them or they will not have any letters between them. We had earlier counted, when both A's were together, this was the total number of cases possible. Out of the total, these many were when both A's are together. Once we have this, we can just count the number of cases remaining, which will be the cases when both A's are separate. Let's take a look. 10, 3, 2. Let's just do this in the corner. Make sure that this is actually the same. So we are subtracting from our total number of words the number of cases when both A's were together, which was 10 factorial by 3 factorial 2 factorial. Again, we are looking at multiple ways of solving a problem. The more chapters you will, the more topics you will learn in this chapter, the more number of ways are there to solve a problem, as long as you are not counting any case again, you're not missing any case. Then you will get the same answer. It's very important to understand all of those methods so that in the exam, whichever method comes to you first, you are able to use it to get the right answer. Anyway, coming back here. Now just some manipulations here. We take this common. So what is left in the first one? 11. And here we have taken this common, so the denominator becomes this. In order to make it this, we multiply 2 factorial with the numerator and denominator. So 11 minus 2. So this is 9 factorial by 3 factorial, 2 factorial into, I took 10 out, so remaining 9 factorial, and then 10 and 9 from here, and this remaining 2. So this is the same as this, 9 factorial by 3 factorial 2 factorial, and then 10 into 9 by 2 is nothing but 10c2, right? If you multiply this by 8 factorial with in the numerator and denominator, we get 10c2. So that is why both ways are correct. If we had already calculated this and this, then you should not have to calculate this again, you can just subtract. But if this were an independent question, if you see just this problem, then this is the quicker way of finding this, because otherwise you will have to calculate multiple things. Now coming back, let's take a look at when no two i's are together. Now we cannot use the same method. We did see, okay, we did not see, but doesn't matter. Let's say we had seen when all i's are together. In that case, if we just subtract those cases when all i's are together, do we get the case when no two i's are together? No, because there's a third case possible when 2 of the i's are together and 1 is separate, right? So how many cases do we have with the i's? Because there are 3 i's, either all of them are together or 2 of them are together and there are some letters between them and then the third I, or all 3 of them are separate. So now we can't just subtract total number of cases when the 3 i's are together from the total number of words possible, because this is also there. We want to calculate this case when the 3 i's are separate. So we'll use the gap method directly now, just like before. We arrange the remaining 4 plus 2 plus 2, 8. So 8 factorial divided by any repetitions? Yes. 2 factorial, 2 factorial. And then we have to place the 3 i's. We have arranged 8. So we have 9 gaps. So 9C3. And this is your answer. Okay. Now, the next condition is all vowels and consonants are alternate. How many vowels do we have? 3 plus 2 plus 1, 6 vowels and 5 consonants, right? So that means in the 11 letters, we need to have vowel, consonant, no other way, right? Because they have to be alternate. So it will start with a vowel, then consonant, then vowel, then consonant, and like this. So 5 consonants and 6 vowels. Two, 3, 4, 5, 6. Something like this. Correct? Now, bache, just for future reference, this is a different number of consonants and vowels here, right? We have 6, we have more vowels, less consonants. If they were equal, then we could not say that it will start with a vowel. Then it could also start with a consonant. But in this case, if it started with a consonant, we will have 2 vowels remaining at the end. So it has to start with a vowel. When one thing is extra, then it will start with that. But if both are equal, then we have to consider both the cases. We will do a 2 factorial to count all of them. Okay. Now coming back here, we have 6 vowels, right? 6 positions. We know vowels have to go here. So if we just arrange the vowels in the order, then we get one particular arrangement of vowels. That means we get V1, V2, V3 and we place them here. Similarly, for the remaining consonants, we just have to arrange them in these 5 spaces. So we arrange the the vowels 6 factorial by 3 factorial and 2 factorial, and then O is unique. And we arrange the consonants 5 factorial divided by, there's a repetition here as well, and just like that we can solve such a problem. Okay, but if this weren't true, if there were, let's say, 5 vowels and 5 consonants, then we would multiply this with a 2 factorial to count the number of cases when it starts with a consonant instead of a vowel. Clear? Okay. Now last one. 2 eyes are together but separated from third eye. That means this case, when these two eyes are together but this eye is separate. Now it's using bundle method to make sure 2 of them are together and the gap method to make sure the third eye is separate. So what we are going to do is, we are going to split the 3 eyes into 2 units, 2 bundles. One is I1 which has 1 eye and one is I2 which has 2 eyes. Okay, these are now different. I1 is different from I2. They are 2 eyes is different from 1 eye, right? So that means now we have to arrange how many units? 2 from here and the remaining 8 from here. So now we have to arrange 10 objects. How many repetitions are there? I'm sorry. Yeah. No, we can't just do that, because we have to keep these separate as well. So what we are going to do? We are going to arrange the remaining. I'm so sorry, Vijay. We are going to arrange the remaining. That means we have to arrange 4 plus 4, 8. We will arrange these 8 factorial by 2 factorial, 2 factorial, just like before. But now instead of choosing 3 from the remaining 9 gaps, we choose 2 from the 9 gaps to place I1 and I2. But now the order matters. If you remember the M1, M2, when they were distinct books, when the order mattered, we had to arrange those M's in those gaps. So we will multiply this 2 factorial to arrange I1 and I2. The I2 could be first or I1 can be first. Okay, so just like this case, we first arrange the remaining 8 objects, the remaining 8 letters, and then instead of finding 3 spaces, we find 2 spaces, because 1 unit is there and 1 unit is this. So we select 2 spaces and then the order can be different. It may be I1 first and then I2, or I2 on the left, I1 after that. So 2 factorial. Okay. Yeah. Now, in how many ways 5 boys and 3 girls stand in a queue such that no 2 girls are together? That means all girls are separate. This is a gap method problem. So we arrange the remaining 5 boys, 5 factorial, and out of those 6 gaps, we have arranged 5 boys, so 1 extra, 6 gaps. From those 6, we find 3 for these 3 girls, and then we have to arrange these 3 girls, so 3 factorial. Okay, directly applying this, not repeating this. Now, by now you are very clear on the theory. Let's look at the second case, when exactly 2 girls are together. Just like the I's, G1, G2 is 1 unit, G3 is 1 unit. Also, G2, G3 can be 1 unit and G1 can be another unit, or G1, G3 can be 1 unit and G2 can be another unit. So in total, how many ways can we do this to select 2 girls, the 2 girls which are going to be together? 3C2, right? Out of 3 we have to select 2, so there are 3 ways of choosing 2 girls out of that. So first we form the unit. Okay, now that we have the unit, in this case again it can be G1, G2 or G2, G1, G3, G2, like this. So within the unit there can be 2 factorial arrangements. Now we have the unit. Okay, now let's arrange these. 2 girls are together, the third is separate, so the gap method is there, which means first we arrange the boys, and out of those 6 gaps we choose 2. Instead of 3 now we choose 2, just like before, because 1 gap is for this unit, 1 gap is for the remaining girl, to make sure that these 2 units are placed separately. They are never together. So we place them in the gaps. So 6C2. But because these units are not identical, they are different. So another 2 factorial to arrange these 2 units. Alright. So this is the final answer. Just make sure you're counting every case and keep multiplying, because for each of these 6C2 there will be 2 possible arrangements, the unit first and then the independent girl, or the independent girl on the left and then the unit together. Alright, so this is how we can calculate. Now let's move on to our last problem. I want you to try this first. I'm going to give you some time and then we're going to discuss the solution. So it's based on everything we've done so far. N be the number of ways in which 5 girls and 5 boys can stand in a queue in such a way that all the girls stand consecutively. All the girls are together. That means there is one bundle containing all the girls and the boys can be anywhere. That is N. M is the number of ways in which they can stand in a queue in such a way that exactly 4 girls can stand consecutively. 4 are bundled up together, 1 is separate. There has to be a gap between this and this, otherwise 5 girls will end up standing next to each other. We want exactly 4 and then a boy and then a girl, or 1 girl and then at least 1 boy and then the 4 ones. Okay, so that is M. So we have to tell what M by N is. So first of all, what is N? Easier? Just tell me in the answers quickly. Even in factorial terms, because we anyway have to divide it, so it's okay when it gets cancelled. You don't have to calculate exactly, just in the factorial terms. We have arranged, we have bundled the 5 girls together. Now how many arrangements do we have? 5 boys plus 1 bundle of girls. So 6 factorial, right? But within that bundle, within that unit, girls can have different arrangements. So into 5 factorial. That is N. Right? Did everyone get this answer? That is very sweet, bache. I hope you're not compromising your other classes, but I'm glad that you're liking this class and you're prioritizing this class. Anyway, did you get this answer? Good. So, now time for counting M. Just like the eyes thing, the girls think, exactly the same way we are forming the bundle. So firstly, we have to form the group of 4 girls. We have to select which 4 girls are standing together, right? And then rearrange them. So these are all our units. Once we have our unit, then we have to first arrange the boys. So we arrange them, 5 factorial. Now out of the 6 gaps, because we've arranged the boys, out of the 6 gaps, we have to select 2 gaps to fill 1 unit of 4 girls and the 5th remaining girl. So 6C2. And then because the unit and the independent girl are distinct, we have to arrange them as well. And this is our M. Correct? 5 into 4 factorial into 5 factorial, 62 into 2 factorial. Perfect. Very good, bache. So now we just have to calculate M by N. So we divide this entire thing by 6 factorial and 5 factorial. Right? So 5 factorial gets cancelled. And we can write 6 factorial as 6 into 5 into 4 factorial. Correct? 4 factorial gets cancelled. Then 5C4 is nothing but 5 by 4 factorial into 1 factorial. So this is 5. So we cancel this with this 5. Now what is remaining? 6C2. In the numerator, what is remaining? 6C2, that is 6 into 5 by 2 into 2 factorial into 2. Even that gets cancelled. Divided by what's in the denominator? Only 6. So what's left? 5. I hope everyone got this answer. Yes? So it's just as important to be careful with your calculations, especially with factorial and combination operator, because I know this is also very new to you. So even if you got this answer, it's also important to get to this answer. To get these calculations right, just with practice, you'll get the hang of it. You'll be very, very comfortable with it. This is not very difficult, right? This is the easiest part. Coming up with this whole thing was the hardest part, and I know you all can do it. So just make sure you revise all of what we did today. It's all very logical. Do not try to memorize any of it. Just try to understand. Combinatorics cannot be memorized. Combinatorics is just something that you have to understand logically, and it will be very easy for you to come up with the answer for any problem if you understand it completely. Okay? So I will see you in the next class. Make sure everything that we have covered so far, it's been very basic, I know, but you are able to solve any of those problems so that in the next class, whenever we are applying any of the old things, you're not struggling with that. And if you haven't done the practice questions from the previous class yet, make sure you do it. I've also shared the answers there. And you have to also think of 7C2, why that thing was happening earlier in our problem, right? So I will see you in the next class. Bye.